Hello everyone here in Helsinki. Hello everyone at home as well. And thanks for being here. So we have already our agenda, and I hope at home you were able to see the agenda. I'm Marco Savarese, and this is a workshop organized by CoMPaSS, a new CoMPaSS-NMD, a new funded project. We will have several interesting topics today and hopefully a fruitful discussion. I will let Professor Tupler briefly say hi as well. Please, if you can join here because the camera will be on the computer.
Thank you very much for attending this meeting, especially participants who came and took the time to stay with us. This is a meeting after over 1 year, and we will start seeing what we built. And this, in my mind, and of course, I hope at the end will be true. I hope we will proceed and we lay the basis for the future work and to get, of course, towards what we want to find, and which means to understand more about this neuromuscular disorder and provide new tools for patients to be managed. Thank you very much to everybody, and we can start, and thank you very much.
I will introduce the first speaker, Professor Wood from Helsinki, Tampere, and Vaasa. He will describe, let's say, the needs from a clinical point of view, the needs of patients with a neuromuscular disorder from a clinical point of view, and just a technical comment. Feel free to ask questions also from home. We have a speaker and we will be able to hear what we are asking. So please just join the discussion as you were here in Helsinki. I will share the presentation. Well, just a second to be sure that it's the correct one. Please, the floor is yours.
Thank you, Marco, and happy to see you all here in Vaasa. Many good friends. I was hoping to see you at one point also in Vaasa, at my hometown. Some of you have been there, but not everybody. But Helsinki is good as well. Unfortunately, I'm not able to stay with you all the day because I'm on my way to Cairo right now. So I have to leave after my talk, more or less. But we will see. So the points raised in the project are very well taken and well sort of formulated. The big aim is, of course, to find a solution for the cases that we currently do not have a final diagnosis for, even if they, for sure, many of them are genetic in a sense. And just providing diagnosis, but also finding the molecular mechanisms as to then go on further for the therapeutics. That's all well known to you. So why is the diagnosis so important for the patient care? Well, you know, without a final diagnosis, everything is more or less open and uncertain. Any sort of doing in the clinics for the patients is not necessarily wrong, but not fully correct, because it can lead to wrong treatments if you, in the worst case, if you don't have the final diagnosis. And more often, we have a sort of lack of measures to contradict complications of the disease. We have many genetic diseases which go with later cardiac issues, and if you don't know about these in time, you can't take measures. And for the families, without the final diagnosis, What is genetic counseling in that case? It's nothing. Can you do prenatal diagnostics for the next child? No. And also there is no correct prognosis for the patient. And that's a problematic point, because psychologically, to have a progressive muscle disease, neuromuscular disorder, and you don't know what will happen because you don't have a final diagnosis. You don't know if you will die with this, what will happen in 5 years, and you don't have any control. If you have the diagnosis, you have some control. You know what, in a sense, will be. And that's my personal experience. Even if I provide patients the diagnosis that they will die, maybe not early, but late with that disease, they are happy to have the diagnosis. They are so relieved to have the diagnosis, even if we can't do anything about it at the moment. So that's for sure. And a couple of examples. Elderly man, progressive proximal lower limb weakness from age 50, had high CK levels and was diagnosed with polymyositis. And after more than 10 years, the rheumatologist consults and asks what to do, because the long-term steroid therapy has not given any benefit. So I asked for the muscle MRI, and here are the images. There is no myositis. And directly by looking at that, I already had ideas what that could be, and that proved correct. So it was anophyte limb girdle disease. Another example, even more tricky case, young Norwegian girl, rough pains in the legs at age 11, high CK levels, biopsy not diagnostic, no infiltrates, no increase of MHC class 1. Antibody panel was negative, but they still thought she had dermatomyositis and had steroids and methotrexate therapy without any response. A new biopsy, no clear myositis, but there was fiber necrosis. So was it a dystrophy? CK still in the thousands, and progressive weakness and loss of walking at the age of 14.
Sorry, just a technical problem. The slides are not changing online, as always.
So
We will have to
back to the,
yes.
it's the same issue.
As always, yes.
Yeah.
What about now? Please check that. If we move, can you check? Okay.
Okay.
Yes, sorry.
Okay,
Please.
now. Okay, so very problematic situation for a young girl. And I again requested the MRI. There is no muscular dystrophy explaining the loss of walking, but there is minor but still increase of stir signals, so meaning edema in some quadriceps muscles, and that made me already think of the not completely new but relatively new type of disease, the antibody HNCR antibody, and that was what I don't see
Yeah, I'm glad to
the line on the side. So that was the correct guess. Girl, this was previously not included in the antibody panels. Now it's more or less there in many places. And she had IVIG with good response, and she's walking again. So just telling how much the correct diagnosis means. It means life for many of the patients. These examples were based on the clinician's experience, of course. to know where to go when in difficult cases. But you can't have all neuromuscular patients seen by experienced neuromuscular clinicians who have experience from 30, 40 years back in time. So we need other tools. But and still have many patients with wrong diagnosis. Here is just a list of some of during the recent years. So what is beyond the monogenic neuromuscular diseases that we more or less find diagnosis for at the moment in the majority of cases maybe. So we have complexities, and I take ALS as an example. Traditionally, it's not genetic, but we have the experience in Finland that is opposite. So 1/3 of all ALS in Finland is explained by C9orf and SOD1 mutation. And of course, my idea is directly, what about the rest? So has to be something with genes as well. And more than 40 genes are associated with ALS. And we already have some examples of oligogenic mechanisms where different genes come together and may explain the expression of the disease. We have ALS genes in the range of multisystem proteinopathies, MSPs, where the same gene in one family makes ALS, in another family makes limb-vacuolar myopathy, in a third family maybe Paget disease or combinations of these. A long range of MSP genes. What is the reason for this variation of phenotypes and targeted organ tissue? We have some ideas from our experience with the first digenic neuromuscular diseases. We have identified the TIA1 sequestosome combination, and together with the Newcastle people here, the combination of truncating titin variants in heterozygosity with SRPK3. Again, telling that if you have peculiarities, not really following the monogenic rule of expression of disease, then you probably have other interfering combinations. And of course, FSHD with methylation, I think, is well in that spectrum as well. IBM, inclusion body myositis, what is there? They have heavy association with HLA loci, but the explanation for the degenerative part of that disease is still open. And of course, we hope that multi-omics will help to clarify and indicate profile groups where we then can start to look at these combinations of genetic factors. Just some examples of use of MRI. It provides not only diagnostic insight, but also on the background pathomechanism, as with the FSHD. Here, telling about the edema, inflammatory edema in the early stages of disease affection in muscle. But of course, if I just would see this picture of a neuromuscular patient, I would probably guess the diagnosis, because no other disease can cause this asymmetric loss of rectus femoris and adductor longus. So high diagnostic value. In the case of myotonic dystrophies, we have several types, two major, congenital form and a normal adult onset form. And these are completely different in terms of background for muscle weakness. these two patients are equally weak for their age, but the congenital does not have any loss of muscle, but there is loss of contractility as another background, and the loss of muscle in the adult onset patient. The diagnostic interest of MRI for IBM is also very high. It's almost pathognomonic, with the edema signal in the same places where you have the atrophy and degenerative change. Of course, we have been using MRIs to sort of understand the meaning of unknown variants in previously known muscle genes. We have a new variant in a known muscle gene, and we have to sort of have tools to see, could that be the cause of the disease? And then we, of course, use MRI patterns for sort of these associations. In the group of distal myopathies, we have made 3 major categories. We have one group of genes that take more the anterior part of the lower leg muscles than the posterior. And we have another group that take more the calf muscles than the anterior part of the muscles. And we have another group that take both sides. And these can be used directly to check if a variant in a known gene may fit some of these patterns or not. Of course, titin is always the most tricky of them. Also here, just to show what the common mutation in Finland, the last exon, causes in heterozygosity, just the anterior compartment problem more or less, whereas in homozygosity, all muscles are lost at the same age. More complexities with this, of course, if we have that Finnish founder mutation or the Italian founder mutation in combination with the recessive variant in the A band, completely different picture. Nothing in the anterior, but solely is heavily lost, and the quadriceps severely affected. And if we have recessive variants in the 2 last exons, we have an early onset, a juvenile onset, recessive distal titinopathy. Again, with heavily more soleus and peroneal than what we see with the dominant form. H-MERF is the most spectacular of them all, so hereditary myopathy with early respiratory failure, diagnostic pathognomonic pattern of muscle involvement, where you have the combination of obturatorius, semitendinosus, and tibialis posterior. The common variant in UK also causes early anterior compartment, but very peculiar. All these with the same gene, and even if we go to the congenital forms of titinopathies, very many different types. So here, just to show you high selectivity of some muscles completely lost, more or less. This is congenital amyoplasia. So these muscles never developed. They were not there from the beginning, whereas other muscles developed. This is to tell you that we have the complex region in titin, where some exons are heavily important for prenatal versions of muscles, but are not expressed after birth. And again, you have the heavy amyoplasia, but a non-progressive course, because the mutations are not active after birth. And these complexities we have to also consider with when trying to use new parameters to understand the patterns. And here, just to show you that all congenital tendinopathies are not these amyoplasias, but are some of them are then instead progressive in the later course. Just a few words. How many minutes do I have?
Still,
Okay.
still you have.
I don't see any watching.
No,
so,
no, I
okay,
guess,
yeah.
I don't know, but
The neurogenic mechanism causing neuromuscular disease. Okay, we need to know at least something what happens. If you have an acute neurogenic lesion peripheral, you have a edema in the third muscle, which looks like inflammatory, but it's not. It's vasodilatation causing that increase of water in that muscle in the acute, very acute stage. In the very chronic stage, a completely different picture. This is Kennedy spinal and bulbar muscular atrophy. You see all muscles are affected, heavily dispersed with a neurogenic sort of type of mechanism. But we can have other problems which you need to be very difficult to then combine with these proxies you will have to assess muscle images. If the problem occurs at the developmental stage, you will have a picture looking like a muscular dystrophy, with some muscles bad and other muscles more or less totally gone. And you have the same also with genetic diseases like the ICD mutated SMALET, where you have this dystrophic-like picture. You would guess in the first place this is a muscular dystrophy, but it's not. And there are some peculiarities. So there are small islands with remnants of muscle within the muscle that is otherwise totally gone. More complexities from the clinical point of view. We have some genes causing the same time damage to the nerve and the muscle, but separately to both tissues. And the start is neurogenic. So you see in the younger, you see the neurogenic type of pattern in the calf muscles. And also something in the soles. But later on, the myopathic part takes over and sort of makes it a dystrophic picture. And you even on biopsy, you have the combination of both myopathic lesions and neurogenic small group angular atrophies. Just a couple of words on the biopsy and the pathology. I would guess, and it is more difficult than MRI because of less standardized techniques. What was the age of the patient when the muscle biopsy was taken? Duration of the disease? What are the routine histopathological procedures? Can immunostainings be used? Western blotting material on the results? Just a couple of examples. Many labs still use ATPase for fiber type grouping to see the 3 different fiber types in different pHs. But there are problems with that technique. It fades over time, so it's very old glasses to see. We developed a new technique with double immunohistochemistry to see all 3 fiber types on just one slide. And the interest is beyond that the easy part, because in some diseases you have some certain specific findings to take out with that technique, like in myotonic dystrophy type 2, the high amount of highly atrophic nuclear clamp type 2 fibers, which you can see here. And these cannot be seen by ATPase technique because ATPase also stains capillaries and blurs the situation. And of course, when you take a new technique, you see new things. And this is just an example of what we saw, a new disease, just by seeing the lack of type 2A fibers. I think I will stop.
Yeah, a few minutes. You can go towards the conclusion.
Yeah. So no, I think I will just point out that there will be complexities in using sort of platforms to make a clever decision based on AI. But of course, we have to start somewhere and then take in these complex issues also from the clinical point of view to be able to address them. Thank you.
Thank you so much. So the floor is open for discussion. Any question online, please feel free to write in the chat. Elisabetta, you can follow eventually the chat, or just to open your mic and ask questions. What about here in the room? Any question? I have one, and it's on the genetic monogenic versus non-monogenic. Do you have in mind any numbers? So what would you expect? What is behind the missing hereditability, or what is behind the missing diagnosis?
One thing is that in the most severe group of muscle diseases, the progressive muscular dystrophies, we probably have more monogenic forms. But when we go to the milder forms, there is much wider sort of variation. And in some cases, it's even difficult to know which family members really are affected or not. If you go to myalgia with some CK elevations, you are in trouble. So I think it is good to start with the sort of more better clarified forms and develop the techniques with that, and then see how it can be applied to milder forms.
Please.
Just one comment. So thank you very much for sharing your thoughts here. I love the MRIs. You said it's important that we consider, for example, application of AI, because not every neuromuscular patient can be seen by a neuromuscular specialist. In these discussions, I more and more feel that we need to make a very strong case that any suspicion of a neuromuscular disease where you're uncertain, you need to involve a neuromuscular specialist. I think that ultimately, that is actually a really important message. Particularly with the treatment modalities that are coming up now, you need someone. I agree that the myotonic dystrophies and FSHD and maybe dystrophinopathies or SMA patients can probably be diagnosed by non-specialists. But when it comes to care and management, still, I think, the neuromuscular specialist is becoming more important. I think that's also something that our community needs to emphasize.
But then we need to train more people.
Yeah, no, exactly. Jan,
for the whole world.
Yeah, I think rather than saying, well, trying to train non-specialists in, making diagnoses and looking after patients, I think, we need to put efforts into getting more neuromuscular. Because I think your talk also just showed the complexity. It's it's not getting simpler, it's getting more complicated.
Yes. No. Yes.
If I can make a comment, I think we should raise the awareness of the complexity, because this is the real point. Because how many times we see overlapping phenotypes and then we go in a direction and we find something, or in another, there is a contradiction. It is really, I think it is very, very important to make people aware and that it is difficult and you cannot really think about a simple explanation. And the family, yeah, as you said.
But nevertheless, I think standardization is an issue.
Yeah.
Starting from the clinical point of view, so that we do a better phenotyping, train more people on phenotyping, but getting also a pattern that we can analyze by AI technology. And the same what we are doing now here in this consortium is really looking at, as you well taken point on biopsies as well. Also there we lack any standardization currently. So we have our patterns, our all teaching book patterns we still use in a way, and we adopt to single genes then a bit our pathology, but we all know that this is limited to just then one little tiny piece of muscle. And I think the combination with MRI will really help us to get this clinical information, muscle tissue, MRI, and genetics on top. And this will guide us feeding back to the phenotype. So which phenotypes we have perhaps overlooked and fit into the pattern.
Yes, and I also see the potential in the group of not diagnosed ones, where we can then use the profile from all these data to see which cases, single cases, fit together, to try to look into that group with other eyes.
And there's the element I see for AI, that really our caveats we have in imaging, we have in biopsy, in genetics, and also in clinical phenotype can help to come close a bit more on the caveats we have still in all the short techniques.
Thank you so much.
And sorry, I have to leave.
Speaker. Yes, thank you. We can move to the second speaker. Just a second. Thank you again. So our second speaker is Dr. Hackman from the Folkhälsan Research Center here in Helsinki. Dr. Hackman is an administrative group leader here at Folkhälsan, and he will discuss now the genetic aspects concerning the needs in the field. Just a short, can you recognize your own CoMPaSS?
This one, yes. There.
Yes, but I want to it like this because I know that.
Yeah. Okay.
And then we will look from here.
Yeah. And then I just go down here.
Yes, yes, but I will want to.
Yeah.
Yeah, maybe it's easier
Mm-hmm.
like that.
Yeah. Yeah. Take away the. Yes.
Let's see what happens if.
If you, there is good. No, is good.
Yes.
Yeah.
So please, can you
Yes.
check your line? No. Yeah.
Okay.
Just a second.
Mm-hmm.
Now you can see the line. That's what. Please.
Okay, so good morning, everybody, and welcome to Finland and Helsinki. And we have an unusually good weather now. We have had a very good summer, but this time of year is very uncertain, the weather usually. But today it's really nice, and I guess it will be this week. Anyway, so I know maybe about half of you at least we have seen before in different meetings, or more than half of you actually. So, but anyway, so I'm going to talk about the perspective from the molecular geneticist point of view of this sort of this. No, it doesn't. Oh, okay. Yeah. So we talked about that, how many patients we do have and so on, and it's very hard to estimate because of different reasons, and not all of them are clean, but there may be something like in Finland, only 20,000 people that are somehow affected by inherited neuromuscular disorders. So it's a lot of people even though for the individual diseases, it's not that many. And we have, of course, disease-causing mutations in hundreds of different genes that have been associated, but still a significant number of patients are without a genetic diagnosis or a diagnosis, despite the increasing molecular genetic knowledge obtained. So it's clear that effective therapeutic options are very scarce. So there is a big need for continued research leading to more knowledge about the disease mechanism, and therefore also to improve diagnostics and therapies. So then many of you are aware of this, but I'm going to talk a little, just one slide about this Finnish disease inheritance. So Finland has 37 at least genetic diseases which are more usual or this specific kind or version is only existing in Finland. And why do you think that is? And most of you know it. And it's because these countries have been an isolate. So there's been small groups of people moving in here, and they have then become the big population. Of course, we have migration from other countries and much more nowadays, so it's not really true in the same way. But and then we have this sort of, like hungers and diseases and all of this that have decreased the population also at some point. So this is why we are really an isolate still, sort of. And that's very nice from the genetic researchers' point of view, because you find a lot of families where you can see also recessive disorders and so on. And this Finnish disease inheritance, here's a list of the diseases. That's in Swedish, but you can maybe understand most of them, because Swedish and English are not that far from each other. But then I followed, because at the Folkhälsan Research Center, during the years, we have actually been involved in research on many of these diseases, and I covered them in red here. So you can see that roughly about half of these disorders we have been somehow involved in. It doesn't mean that we have always found the first mutation in them, but we have been involved, and in some cases we have found the first mutation also. So it's very nice for that we have managed to do this. And but then I go back in time a little bit. And don't worry, I'm not going to stay back in time, but this is the old, let's say, anecdote that I'm also always telling, that when I began to work here, we were, because of linkage analysis of tibial muscular dystrophy patients and families, we were suspecting that the mutation would lie in the gene titin. As you know, it's a super big gene, and it's not easy to analyze. And especially at those times, when there was only Sanger sequencing, it was really slow. And we began from the beginning to do the sequencing, and it took a lot of time. And then we finally found it in the last end of the titin molecule. So we were almost giving up at some point there. But anyway, so that was, of course, it was good that we went through the whole titin gene so that we didn't miss anything else. But this is just nice to tell as an anecdote that sometimes it can go like this. And as you know, I mean, there's a lot of, because it's a very big gene, there's a lot of disorders that are actually associated with titin. And I'm not going through them, and actually, Bjarne mentioned, the TMD, the LGMD he mentioned, I think, and also the H-MRF and so on, but I'm not going through this anymore. But anyway, so in the beginning, we had the Sanger sequencing, and then you could sequence hundreds of bases in a few hours, which was thought of being sort of fast. But then fortunately, we developed these methods, the next generation sequencing methods in the 2010s, and then suddenly you could sequence hundreds of millions of bases in a few hours, basically. And the other good thing was that the costs came down. And this is only until 2021. There has been a development after that also. But in the beginning, it was super expensive to do this sequencing. But because of the next generation sequencing methods and so on, it became affordable to do it. And that was really good. And because of these methods, then we could suddenly sequence all of these big genes that had been really difficult to sequence before, like titine, nebulin, DMD, obscurin, and many other ones. And there's just then a picture of the scheme of the titine gene with sort of points where you can find mutations associated with different disorders. And this is not updated. This is an old one, so it looks different nowadays. Anyway, so the fact that the sequencing methods were developed was really good, and we could get, data very fast. But big amount of data are not so easy to analyze, of course. Fortunately, bioinformatics have improved a lot in recent years, so it's much more easy now than 10 years ago to do this. But there is still a need for increased amount of bioinformaticians or people that understand bioinformatics. It's very good to have people who understand both genetics and bioinformatics. Unfortunately, we have these people nowadays. But then, of course, we have also some online programs which can do bioinformatic analysis, like Uformatics. There's many more, but I just mentioned this because we have used that one. So this is not a commercial for that one. Anyway, and then another very important thing is that we have these international initiatives, organizations with databases, registries, biobanks, and services. And you know all of these organizations, and some of them are not working so actively anymore and so on, but I mentioned it here because all of them have been important for us. But then just to take some examples. So if you look at one classic example, which was slightly difficult, and don't worry, I'm going to talk and then jump forward to other things. But anyway, so we had this Finnish family with an adult onset dominant myopathy, but the problem was that we find a linkage to 2 loci, not only to 1, and we didn't actually, and we struggled with that for years, and we didn't find anything interesting in either one of these areas with the methods we had at that time. We did some years ago in 2020, we did again a SNP array and a linkage and tried again to get into this because we had a lot of new methods. Again, we found the same associated loci, but again, we didn't find directly anything that was clearly doing this. So we did the VES and we did MyoCap, this targeted NGS and VGS, but still we didn't find anything. But then came the fact that the bioinformatics were developing. And we did then a CNEVID analysis done by Salla, nowadays Rusanen in our group, that she created sort of a combo of methods to analyze CNVs. And then when she did that, she found a small deletion on the HNRNPA1 gene that included exon 9 from the gene. And this was not found in any CNV populations in the databases. After that, we did also RNA-seq, because now we had RNA-seq as a method also, of course, available. And then we found actually that there was that you could see that the mutated gene was expressed on the RNA level, lacking this exon. And that was also expressed on the protein level, and so we found the mutation causing this disorder. We were very happy about that. These are just some examples of found variants in genes causing NMD disorders by our group at Folkhälsan during the years. So I think it's quite a nice amount of genes we have, of mutations we have found. Of course, this has led to available diagnostics and to better therapies. But then we have another example. Again, one slightly similar. This was from Germany. And there we also had sort of 2 linked areas, but no interesting genes were segregating in these were found. And we didn't find anything very clearly predicted to affect splicing or anything. And then we did a lot of RNA-seq, and we found something, but not really anything. There was like this zinc finger that was that had a upregulated expression and so on. And then we did some optical genomics for this, as some of you know, and we found something that could have been potentially interesting, but it was not segregating with the disease. And then we did proteomics with Andreas Roos groups, and again we found something. And then I'm not going into it now, but then actually doing all this, we found something that might also be causing this disease. But in this case, our theory now is that it's a digenic disease with one maybe more rare component and one more usual component. But I'm not going into it because we are still in the middle of wrapping it up. But anyway, so this is an example of what Bjarne talked about also, that we have this digenic and oligogenic diseases, and they are becoming more because we have solved the easy cases, the low-hanging fruits, and the ones that are still remaining are often something slightly more complicated. So, but anyway, so what we do nowadays, usually we have this combo that we always use usually use the SNP array with the GVAS, because then you can narrow down the linked regions. And even if it's an old method, it's quite good still for this. But then we do the VES or the GS or long-read sequencing, RNA-seq, and if needed, we do optical genomics and proteomics and so on. And then when we find something that we really think is the causative, then we can go to functional studies like cells and zebrafish and so on to prove it. But because now, I mean, very often it's still like banging your head in the wall when you are a geneticist working with this. But now maybe we have new solutions that can help in this. And this is, of course, the AI. And I know that Tuomas Hartonen, I don't know where you are, if he here. Okay, hey. So you're going to talk much more about this, but I'm just going to explain what it is. And I'm not an expert on AI at all. We have one person in your group that is actually doing AI. Victoria sitting there behind you. But anyway, so I'm just explaining what AI is. And AI is intelligence exhibited by machines. And this I picked from some reviews that I have been reading about it. But it's a good definition, I think. Or you can also describe as machines that mimic cognitive functions that are associated with the human mind related to learning and problem solving. I think this is also a good explanation of how you can see it. There have been groups in European Commission that says that AI refers to system designed by humans, which given a task can interact with the physical or the digital world by interpreting structured or unstructured data and to reason based on the knowledge obtained. So its final objective of the AI is to present the best actions to take according to predefined parameters to achieve the initial proposed objective. And then some more stuff about, so I hope I'm not talking much about what you are talking. I think you are going completely more deeply into this. But already AI has demonstrated potential in improving the efficiency of diagnosis and treatment in the world in different disorders. And machine learning allow for the efficient analysis of big data sets in identifying patterns and generating key insights. And this is already also Bjarne mentioned. And therefore it can be of big interest and help in research projects. And we are going more into this later also. So, and predictions can be made for medical diagnosis and personalized treatment recommendations. And also it has enabled researchers to train models based on a large data sets and then fine-tune these models on smaller data sets associated with rare diseases. So in conclusion, I hope I was not too fast or too slow. Okay, good. Yes. So we have identified and characterized a large number of causative mutations in genes by NGS methods. and this have led to reliable diagnosis. And by improved bioinformatics in combination with all the methods and also the CMV analysis and repeat expansion analysis and many others, we have also gone forward in finding causative mutations or changes. And RNA-seq is of course very useful, and OGM also is very useful for finding structural mutations. And even if we didn't find the causative mutations, the method worked very well. Epigenetic studies can be performed. I'm not going into them, but this can also be done. And in cases where we find the causative mutations in a gene, then we go to these functional studies. And also that AI is being used more and more in genetics research and diagnostics. But I think there's still a place for humans, I hope. So, yeah. So our goal is, of course, that all patients with neuromuscular disorders could get their diagnosis. And then just listed some of our collaborators. So our group and then I did this Marco Savarese dos Plus group members. So I'm sorry.
Sorry.
Yeah. Okay. Thank you very much.
Thank you so much. Thank you, Peter. Thank you. And once again, if you have questions online, just drop a message or unmute and ask a question. But I have one. I think the good point and very correct point is the one related to bioinformaticians. How do we get bioinformaticians with a knowledge in the field? Would be easier to give them a knowledge, or would be easier to train vice versa? No, people with already knowledge in neuromuscular disorders in bioinformatics. I guess we can have different opinions.
My opinion,
but I think it's crucial.
Yes, my opinion is that I think we need both, but it's good to train people who already have a knowledge about genetics, who are geneticists or clinician geneticists, to train them in bioinformatics.
I had the suspect that was your point of view. Okay. I'm wondering if Johanna's point of view is the same or is opposite.
Yeah.
And it's about more important for particular task.
Yes. Yes, I agree. Yes. Yes.
That's why we need a cooperation.
Yes. Yes. Yes.
You know, it's like with statistics. Everybody thinks it's so simple because you click and you get the result.
No, it's not.
Okay, if something is white and black, you can do it.
Yeah.
And the same with bioinformatics.
Yes.
Then you can learn how to do it, having no background.
Yes.
But these tasks are not easy.
Yes.
So
And
because of that, I think.
But yes, and I agree with you that we need real bioinformatics, but it's good to have these people that sort of make a bridge between geneticists who doesn't know bioinformatics and then the bioinformaticians.
It's important that you need these people who are very well trained in one field.
Yes.
And they seem to cooperate.
Yes.
And they learn the language because now it's about the communication also. Every of those groups, they use different language.
Yeah.
And some other aspects and some other things are important. So in my opinion, we have to do simply interdisciplinary.
Yeah. Yes, I agree.
I think you raised such a good point that this is a good topic for a roundtable we can write down. And maybe we should organize an open discussion on what is the need in the field and how to eventually get it. But please.
If I can add a comment, CoMPaSS is going in this direction because we really think that it is extremely important to create a way to communicate.
Yes, that's right.
Otherwise, the knowledge remain like in separated boxes, and we cannot reach each other. But,
I agree.
Please.
If I can add another comment, this is also the goal of the European Commission when they transfer money to our project. So we are building new skills, we are building new job position, we are building something that is not here in this moment, but it will be. And if we are talking and thinking also about our training and the next autumn school, wow, we are touching deep to this to create a new job, new skills, and new person that can do diagnosis in a different way, in an innovative way, because this is not something like a different and separate boxes, but it's a cross-cutting topic, and we need people that are able to understand both and bring it together.
I agree.
Please, Professor Stoll.
Thank you very much, Peter. I just have a question. So you, at the beginning, you said there are 20,000 patients with neuromuscular disease in Finland,
Yeah.
which is extremely high. I mean,
Yeah, I don't know if it.
times
Yeah,
higher
yes,
than-
yes. Let's say that I don't think. I think it's also like people that may potentially have it and so on. So I think this number, I just got it from some review article. I don't think that it's people who are actively sick, but who may have this. I mean, genetic predisposition or something like this. So it's a very rough analysis that it's something like that amount of people affected somehow by this now or in the future.
My
Yes,
other question,
yeah.
do you have any idea of how many are actually undiagnosed? I mean, just roughly the percent.
Yeah,
But I always feel that
Yes.
the number of undiagnosed patients is exaggerated.
yeah, it might be exaggerated, and it's of course decreasing all the time, but I think it's maybe several tens of percentages. I mean, maybe less than 50% nowadays. I don't know, but it's a lot still.
I guess we are also
I mean,
biased.
but I mean, I'm not a physician, so it's.
We are biased by the fact
Yeah.
that, as you know, we get the difficult to solve.
Yeah.
Yes,
therapies.
yes. And the one point, I mean, that which is higher in these numbers is that we have maybe 2,000 people that have or will have tibial muscular dystrophy. So that already takes it up to another level. And we have some other also that belong to the Finnish disease inheritage, which are neuromuscular. But I'm sure that it's not like that many diagnosed people, but people that are potentially affected or something.
Please.
Well, as the Scandinavian countries are always super well organized with registries and things like that.
Yes,
So do you have so these numbers of 20,000 I also was considering this is really nice.
Yeah,
But the diagnosed, so do you have a registry that is really lining up the diagnosed cases with genetic backgrounds?
I think virtually you could,
Yes,
I
yes.
think Tuomo will discuss, but the
yes.
health records
Yeah.
are
Yes,
there
we
in
have
the
that.
UK.
Yes, and we have this going hundreds of years back in time also, because the churches used to keep
Yes.
track of people and what they died of and stuff like that. So
With some ethical issues right now,
yes,
but they are
yes, and GDPR is not making it easier for any of us.
But thank you so much.
Sorry for that comment.
Just a second. The next, just a second, Tuomo. So the next speaker is Tuomo Hartonen from FIM, which is the Finnish Molecular Medicine Institute, or the Institute for Molecular Medicine in Finland. And Tuomo will discuss on AI and some real applications of AI with registries, real data.
Yeah, at least the real research.
Real research application, that's true.
Not clinical yet.
I will just a second share your screen. Please.
Thank you. Thank you for the introduction. And yes, as you can see from the title, I'm trying to today give you a few examples of applications of AI to large-scale registry data, mostly the Finnish data, and what we have learned in the last couple of years in the data science and genetic epidemiology lab at FIM. And now I need to learn how to switch the slide.
Oh, yeah, because it's slow.
Oh, yeah,
Okay, yeah.
right. Okay, so the DSG lab where I work is led by Associate Professor Andrea Ganna, who was actually the one who was invited to speak here today, but he couldn't come because of other commitments, so you have to do with me. This is our team, picture taken in our lab retreat in a couple of weeks ago. So before going into the examples, I wanted to explain.
No, it's that. Please.
All right. So I wanted to explain a little bit what I mean with these two terms that I put in the title. So AI and large-scale registry data. And I think we already had one definition of AI in the last talk, and I think my definition is not like that much different from it. Basically, in the context of this talk, what I mean when I talk about AI is I view it as a toolbox of different types of methods that learn patterns from data and use this learned information to make predictions and assist in decision making. And there's a vast variety of different types of methods that you can use to implement AI, and they range all the way from what can be called the classical machine learning methods like logistic regression or linear regression, to all the way to these large language models like ChatGPT. And as you can see from this figure here, there are some issues that one needs to consider when you make a decision what type of method you select to model your data. So usually, the more complex the models become, the more training data they require, and they become less interpretable. And so, which means that actually, in many cases, should I admit?
Yes, you can
Yeah.
admit.
Okay.
Yes, sorry.
Okay. So, in many cases, at least in research, we are often very interested in interpretability of the model. So we need to understand what the model actually does with the data. And if the task that we are working with is relatively easy, then it's many times enough to use these kind of simple and more traditional models instead of kind of going with fancy and latest ones. But there's also a place for the fancy and big models, but I think that you should be able to justify why you use these like fancy models that are maybe not so easy to interpret and maybe take more time and resources to train, by actually showing that they perform better than something that is more simpler and more traditional. And then what about the other term that I used, the large-scale registry data? So here, I think a quite good example is the FinRegistry project we have been working with in the lab. So in FinRegistry, we have extensive registry records covering healthcare visits, medications, vaccinations, demographics, family relations, and socioeconomic data. And as you can see from the figure, some of this data goes back in time to 1950s. And in total, this dataset has 7.1 million individuals from Finland, and which means there's more than 6.5 billion records actually in this dataset.
You know how many of them are dead already?
Yeah, about 2 million are a bit more than 2 million are dead. So the regular dataset is built that it includes everyone who is alive and living in Finland in 2010, and then their parents and siblings. But basically, this type of data can be accessed in Finland through the Secondary Use of Data Act. You have to basically contact the FinData, which is the authority that grants permissions to use this type of data for research. One point about the registry data is that it is mostly tabular data, which is also one point that is good to keep in mind when making modeling decisions. For example, we saw a lot of images previously. So in this dataset, for example, we don't have images. But the tabular data can also be quite different in forms. So for example, there is this Kanda laboratory values dataset, which contains more than 600 million laboratory responses, and which means there is
More coffee?
very important things. So there is at least one laboratory measurement for 91% of Finnish population in this dataset, and in this figure you can see the coverage per age. So it's actually quite nice for a lot of the age ranges. All right, so now we perhaps are on the same page of what I mean by AI and what I mean by this registry data. So I'm going to give you some examples from our previous research and kind of some lessons that we have learned from these. And these lessons, I tried to summarize them into these 3 points here. So first is that large-scale registry data contains partly overlapping information, and different variables there can be highly intercorrelated. Biases in the training data of these AI models can lead to the models being unfair towards certain groups of individuals, like minorities. And diagnostic practices differ between countries, which can lead to very different diagnostic code usage in electronic health records between cohorts, which can be problematic if you want to use a model trained in one country in another. So in the first example, I want to show a study we did a couple of years ago where we built this cohort of 3.2 million Finnish individuals and tried to see which factors predicted who was taking the COVID-19 vaccination and who did not. So we collected about 3,000 predictors from the Finnish registries prior the start of the pandemic, and then tried to see which of these predict vaccination uptake. This was basically all of this kind of unbiased in a way that this is all Finnish individuals who were eligible for taking vaccination at the time of the study. And here we did not model the data longitudinally. We just took a snapshot in time and basically looked at what diagnoses and medications and occupation education, so on, people had prior to the baseline, and we made a decision to use XGBoost as our model of choice because it's kind of known to be like the state-of-the-art model for this type of double R data, and it's also quite easy to interpret and very easy to implement. Also, there are very good implementations for it. So we were able to make a model that's quite good at predicting who take the vaccine and who don't. If we look at the top 1% risk group of the individuals that, according to the model, had the highest risk to not vaccinate, those individuals have only 18.8% vaccination coverage. And when we contrast this to the vaccination rate in the entire population, which is 90.3%, we can see that we can really quite nicely find the individuals who are at the highest risk of not vaccinating. And we can also look at which of the variables are most important in predicting who didn't take the vaccine, which is here on the right-hand side. Interestingly, labor income in the year before the pandemic was the most important predictor in the model, even more important than age, for example. Then we also made this experiment that we took each of these data types that we had in the register, we took each of them one by one out from the model. So the model is trained with all data except the one data type that is shown here on the x-axis, and we observed how much worse the predictions became for the model. And actually, as you can see, for many of the data types, the model actually performed as well as the full one when we took out all the variables, which kind of indicates that in these large registries, there's a lot of redundancy in the data, that you can get the same information from multiple places or multiple sources. All right, moving on to the second example, where Andrius from the group used this recurrent neural network architecture, it's a large model with almost 3 million trainable parameters to predict the risk of 1-year mortality. And this model is actually very accurate. And here, from the modeling perspective, what was different to the previous one is that here we actually used the longitudinal nature of the data. So in this right-hand side figure, you can see how the data was. Basically, we have like a vector for each individual per year, which includes all the diagnoses and medications and all this type of different codes for that person. And it was attached to basically age of that person in that year. And this was the input data for the recurrent neural network model. And then, as I said, in my introduction, so we want to justify why we use these more complex models. And we did it by comparing this recurrent neural network architecture to more simple models, like XGBoost and logistic regression that do not use data, model the data longitudinally, but rather take kind of a snapshot of the data and don't consider the time aspect. And we were able to show that the RNN model actually performed better than those. And if we put it in, there's a one way to put it, which is the ROC curve here. So we got the AUC of 0.944 for the RNN model, which was significantly higher than the baseline model, which is here at logistic regression. But also, we put it in other words, if we consider top 5% of individuals with highest predicted risk, 70% of all deaths predicted by the deep learning model were within those 5% top risk group, whereas for the simpler model, only 50% of all deaths were in that 5% risk group. But kind of main point of this paper was that actually the increased accuracy of the model did not come without a price. So one very important aspect to consider, especially if one wants to use deep learning models in clinical work, is the fairness of the models. So that do they make as good predictions for minority groups as they do for majority groups? And here, how we tested this was that we checked what is the performance of the RNN model when we compare two groups that we call like privileged and less privileged groups. So for example, married versus non-married, immigrated versus non-immigrated, individuals with mental health diagnosis and without mental health diagnosis, and individuals with high pension and low pension. And we observed that actually in all of these cases, this complicated recurrent neural network model actually performed worse for the less privileged group. So that's clearly a problem. And moreover, when we look at the geographical distribution of how well the model predicts when we use individuals living in different areas of Finland here, as shown here on the map, where dark colors mean that the predictions are better and light means the predictions are worse, we can clearly see that in the northern and eastern parts of Finland, the model actually does a worse job in predicting. Right. Then the third and the final example that I had for today is a work that actually is not yet published. We're just submitting it. Here, we're basically also working with genetic data. That's only one of these studies. And here our point was that we wanted to see that if we have polygenic risk scores and add on top a predictor that's trained based on the electronic health records, can we actually get better risk prediction for disease onset? And we also wanted to see that if we train these electronic health record-based models in one country and then we transfer the model to another dataset in another country, how well these models perform without any retraining. Here we studied 13 diseases that are high burden diseases, and across 3 biobank studies: UK Biobank from United Kingdom, FinGen from Finland, and Estonia Biobank from Estonia. And the total sample size was almost 850,000 in this case. For the polygenic scores, we used the latest publicly available, largest GWAS summary statistics. And for these phenotype risk scores, we use this phenotype risk score, which is basically an elastic net model that uses all the previous disease diagnosis of the individual to predict the given disease. And one important, I don't know, perhaps not so surprising observation that we made is that the diagnostic code usage varies greatly between countries. Even here, we took the codes, ICD codes in the different countries and mapped them to this common coding system called P-codes. And here on the Venn diagram on the left, we show how they basically are distributed. So we see that only 20% of all these codes actually had more than 1% of prevalence in all of the cohorts. But then, for example, in the Estonian Biobank, 32% of the codes were uniquely used only in the Estonian Biobank. And maybe looking at these examples on the right-hand side makes it a bit more clear. So the prevalence of this same code in the different countries can be like drastically different, even though probably the disease incidences are not so different between Finland and Estonia, for example. So you can imagine that this can make it difficult to take a model trained in one country and use it in another country if the codes that are used to record the diagnosis in the electronic health record are so different. We actually were a bit surprised that we were able to see that some of these models actually transfer quite well between countries. So here we did the experiment that we trained this phenotype risk score model. In this case, we trained it in the Estonia biobank, and then we just take the model weights, no retraining in the Finnish data, and test it in Finland, and compare it to basically compare the association of the score trained in Finland and the score trained in Estonia in this figure. So x-axis is the score trained in Finland, y-axis is the score trained in Estonia, and diagonal line means that they perform equally well, and under diagonal means that the Finnish score performs better, which is obviously what we would expect. And here we have regressed out the effect of age and sex from these scores, so to make the comparison a bit more sensible. But actually quite surprising, for example, atrial fibrillation, which we abbreviate by AF here, you see that the model that was trained in the Estonian biobank actually performs equally well in the Finnish dataset than the model trained in Finland. We can maybe discuss why it is. I have some ideas, but in the interest of time, I'll go forward. So, and finally, we then put together the polygenic score and the phenotype risk score, and we observed that first of all, when we compared those two, we saw that the polygenic score, for example, performed better for prostate cancer and breast cancer, but then phenotype risk score performed better for diseases like gout and type 2 diabetes. And there was very little correlation actually between these two scores. So on the right-hand side, you can see that across all the cohorts and across all the diseases, correlations were very low. So this is 0.1 here, meaning that actually this would make sense to, if you want to make as good stratification or risk prediction as you can, it would make sense to combine these two scores because they contain independent information that is predictive of disease onset. All right. So going back to the take-home messages that I had in the beginning. So first, large-scale registry data contains partly overlapping information and different variables are highly intercorrelated. This can help model transferability and make models more robust against missing data, but it can also make model interpretation challenging. And I think that increasing training data size with more similar type of features is not necessarily going to help so much, but I would think that focusing more on diverse data, like for example, combining the EHR with genetics or with omics or images, is probably give you more performance boost. Second, biases in training data can lead to AI models being unfair towards certain groups of individuals. And so I think, as we saw, it's important to realize that especially these very powerful models can learn even very intricate patterns in the training data. So if we don't test how they perform for different minority groups, for example, there can be large differences that kind of make use of these models unfair in a clinical setting, if we think about that. And the third point I had was that the diagnostic practices differ between countries, which can lead to very different diagnostic code usage in electronic health records between cohorts. And if the model is very dependent on how the training data is encoded, it's likely not well applicable to other cohorts. Okay, I will wrap up.
No, it's fine.
So I think one key question, if we want to combine data from different countries and transfer models, is that can we make the AI models independent of what coding system is used? So I would just quickly say a few words. So I think everybody's aware of ChatGPT and how these large language models have revolutionized, I don't know, the world, maybe not the world, but the way people do work, for example, and stuff like that in the last couple of years. So these type of architectures have already been applied to electronic health records. For example, there's one example here by Artem Shmatko and Moritz Gerstung. And basically how these models work is that they just read in the medical history, you have diagnosis history, and they can then output you basically a prediction of what codes and what time the person is going to encounter in the future. So in collaboration with these authors, we are kind of trying to take these lessons that we have learned and go and research a bit further in, for example, adding more diverse data modalities to these large models, medication purchases, laboratory measurements, testing in large data sets from different European countries, and also looking something I think that Peter was already mentioning, that if these large foundation models are trained on these large data sets, can it actually benefit in predicting rare diseases by learning some patterns? Because for the rare diseases, we don't have enough data to train the large models. So that I think is something that we are also interested in looking at. So thank you very much. I want to thank all the people who have been involved in this research, and thank you for your attention, and sorry for going over time.
Oh, you were perfect. Okay.
Yeah, I think if we can.
Thank you so
I'm
much.
here for the break. So
No, but we can take some question. I think you raised so many important points that we can have a brief discussion. Any question, please?
So when you get data from very different modalities, where you will probably find large blocks of missing data, how do you usually work around that? Do you just impute? Do you train different models and combine outputs?
Yeah, that's a good point. I think it probably depends on the model in question. Like, for example, XGBoost is basically nice in a way that it actually does imputation. Basically, it's kind of inbuilt there, so it learns specific rules for missing data. Yeah, I would say it probably depends a lot on the question you're researching, and then I guess, yeah, question is that if you have some variable that has a very, very high missingness, are you going to include it or not?
Yeah, I'm trying to connect it with the CoMPaSS, because we are collecting data from 3 major modalities, and for most of the patients, we will have information for 1 modality, or 2 modalities.
Yeah.
In that we will have very large blocks of missing data. So that's something we need to think about.
Yeah, that's we haven't done that much imputation in these projects. We have worked a little bit with proteomics, and there we have done imputation, but not so much with the registry data. I guess, yeah, sorry. If I just say briefly, it probably depends on how much data you have available, how much other features you have that you can use for imputation and so on.
For the example 2, where you see the model is working less for some areas in do you have any explanation?
I think we tried to look at it, and one correlation that we observed was that there was a correlation between population density and the performance of the model, but I don't think we were able to kind of understand it further than that. But there's probably that is something that we found.
So could it be due to the number of participants, or for example, to the expertise in or something?
Yeah, it's that data set contains everybody in Finland, so kind of this population density is really the real population density of the individuals living in that area. So there shouldn't be no selection bias in the data, which is nice in a way. But definitely there was this correlation with population density.
So it was one, and then.
So I have 2 questions. The first one is about the heterogeneity of the data sets and that it causes the problem with prediction. Have you tried to construct the balance, let's say the balanced data set for the training to cover up the gap?
If I understood it correctly, I think we have tried it, because what we have tried is that we had this idea of because we saw this, that we have a lot of correlating features. We were trying to do this kind of dimensionality reduction idea. So basically, you can do like a principal component. Yeah.
The objects of the patient. You have probably underrepresentation of those pure or less privileged groups in your data set. And because of that, spatially, the prediction is not as good one. So have you tried to balance the representation of these patients in your data set? Not about the features, about the objects, about the patients.
Yeah, so in the Finnish data, it should contain everybody living in Finland,
Yeah,
but there's
you can sample them for training. Have you tried that?
it's a possibility. Yeah, it's a possibility. We didn't try it for this one yet. But there, and related to that, there's also what relates also to the first question is that there's usually more missing data for example, for individuals that are maybe like immigrants. They are not going to the doctor so much. They don't have so many codes in their electronic health records, and so it's quite complicated. Yeah, actually, the whole this issue.
Please.
So I'd like to listen to your ideas. It's for rare diseases, because you mentioned this as one of the caveats. So we have now quite a bit of rather fragmented and in different languages and highly disease-specific registries, especially for our part of neuromuscular diseases.
Yeah.
So what would be a good idea to lump them together and how to bring them together? Because they are highly specific there, and there's a lot of data sets we have already around the world. But what we need is lumping them again together. And of course, there are a lot of missing data in these registries as well. But do you have any idea how we could do that? How can we label it that it comes to a way for comparison and well, give higher ground on all these already existing data sets?
Yeah, so there is one method that basically, I mean, I'm not so much involved in that paper, but there's Andrea and some collaborators in Germany have been working with, which I like a lot. It's basically so that you actually don't use the codes in the in the registry at all, but you instead use the text description of the code and map those. You take basically the embeddings. So it has learned which words are similar to each other and so on. So basically you just take the code, take the text that describes what this code means, and then it doesn't basically matter what coding system you use, because if you have a code for type 2 diabetes in one coding system and type 2 diabetes in other coding system, the description is probably going to be quite similar. And so then when they put those into the embedding space of ChatGPT, it then actually knows that, okay, these two codes are similar, even though they are from different coding systems. So this is, as I said, I'm not.
There's one major problem in that. I fully agree. So we started that many years ago, but the positive and negative expression, so that there is no disease, no diabetes type 2, or there is, and this is in a lot of languages really difficulty to find out if it's positive connotation or a negative connotation. And if you look at Finnish, it will be very similar to German, because you have a lot of small items that gives you a positive connotation or a negative one. And that's the really problem with these data mining in free text.
I would,
without coding.
Probably especially with free text. I was more thinking about the codes here, because that was where we used it. But probably for free text, it's going to be more difficult.
Do you have free text documents in the?
No, we don't have. I haven't worked with free text actually. So I think there is a possibility if you go to this FinData, you can apply for free text, but we haven't used it.
So therefore that's easier in the registries, because there you have the labeling already. So you don't need to go to these unstructured informations. But for the registries, I think it would be very helpful. You could combine all these data we have around the world, so NMD and in all the different countries as well, they have something. So gaining this information would help also to stratify these large cohorts then, and to get more knowledge on the rare diseases, I guess.
On the same topic, in the registry there are, you said, no imaging.
I think in the Finnish, okay, I might be wrong. We haven't used it. There might be a way to get some imaging data from there, but I'm not aware of it.
Because that would have been, for example, in our field, absolutely
But like, for example, UK Biobank has
They have.
imaging, so they have imaging for a lot of people. But I think the Finnish registries, I think the problem is that it's just so fragmented, the whole healthcare system. So how to put those images
Yeah, I
into
think the
one
cost
place.
will be one of the issues. Okay, if there are no other questions, we are just a few minutes left. But thank you again, Tomo, and he's around, so if you have other questions, comments. And thank you so much also to those who attend online. So we can restart. We have just a small change in the program so that we will start with Dr. Guia Strea. Guia, are you there?
Yes, I'm here.
Hello.
Good morning.
We can hear you, we cannot see you right now.
Oh,
But
okay.
that's fine. I mean, if for any, okay,
Okay.
now we can see you.
I'm here.
And please, can you share the screen?
Yeah. Okay. I not be able to share it.
A second.
Why?
Are you not able to share?
Okay.
Okay, yeah.
Exactly.
Yes, you open your presentation. Yes, thank you.
You see my presentation?
Yeah, we see. Will be larger, but that's
Is
fine. Don't worry.
Yeah.
You can make it a bit larger if possible, but otherwise it's totally fine. I'm sure that. Yes. Okay. Please.
Okay. Okay. Sorry. I don't know what's happened.
Because you are sharing exactly the screen. You should share. Yeah. Okay. Now you can go. Yes.
Perfect.
Please.
Okay. Good morning. I'm Guia Strea. I am a pediatric neurologist and I work at Fondazione Stella Maris.
Wait,
Yeah?
Guia, sorry. We can't hear you very well. Can you get closer to the microphone?
Oh, close my microphone?
No. Get closer. Avvicinate.
Okay.
Yes.
Perfect.
Okay, please.
Okay. I would like to thank the organizer for giving me the opportunity to present our work titled Small Complex Rearrangement in Hint-1 Axonal Neuropathy Neuromyotonia. And this is the table of contents. And I would like to start with a brief introduction about CMT. Sarcomatous disease encompasses a broad spectrum with variable motor, sensory, autonomic, and other organ systems involved. Considerable overlap exists both from phenotypic and genetically point of view. Diagnosis is often complex, and neurologic evaluation, including neuropsychological testing, can help diagnosis and predict patient disability. A definitive molecular diagnosis ensures patient improves care and counsel. Also, next generation sequencing has greatly improved genetic diagnosis. Autosomal recessive inherited mutation in the histidine triad binding protein Hint1 gene are responsible for an axonal Charcot-Marie-Tooth neuropathy associated with neuromyotonia. Herein we describe two brothers where biallelic Hint1 mutations were found following a multidisciplinary approach. Patient 1 came to our attention at 8 years of age for clinical evaluation in moderate intellectual disability, language developmental delay, and some behavioral issues. At first evaluation, motor impairment with frequent falls, pescavo, and dyshypesthenia with reduced osteotendinous reflex were found. Blood tests revealed mildly elevated creatine kinase, and nerve conduction study revealed predominantly axonal polyneuropathy. The brain MRI were normal, and muscle MRI shows the predominant involvement of tibialis anterior and peroneal. Patient 2, the 15 years old brother, presented learning difficulties with hyperactivity and mild incoordination with tiptoe walking too. In this patient, grip myotonic phenomenon was also noted. Considering these characteristics, an NGS panel for gene-related to neuropathy has been conducted, searching for hint1 mutation. The NGS analysis revealed only an heterozygous missense variant, the C355CT, in hint1 that can be classified as likely pathogenic, and Sanger sequencing, as shown in figure 1b, corroborate the presence of this variant in the program. The same variant is also found in his affected brother and in their father. Moreover, this variant has been previously reported in a patient with neuromyotonia and axonal neuropathy. The second variant at first look is unrevealed, but in view of the clinical suspicions, a visual inspection using IGV led us to identify a complex rearrangement located in the region 5.1 UTR exon 1 intro 1, and we can see also an inverted region in the hand of exon 1 and in the initial part of exon of intron 1. Sanger sequencing confirmed this observation. This variant lies on the maternal chromosome and it's present in the affected brother. This novel variant most likely results in a functional loss of one gene copy, but unfortunately, at this moment, we haven't been able to test its effect on cDNA. A further in-depth analysis with optical genome mapping performed in both siblings highlighted the presence of a heterozygous 5q23.3 deletion of approximately 800 BP in patient 1 and patient 2, and in the mother. The deletion is located with a very broad range of 13 kb, which includes exon 1, 2 of the hint1 gene and exon 1 of the LYRM7 gene. Since there are no labels between hint1 and LYRM7, the algorithm detects a putative gene fusion. However, since the two genes are 5 kb apart and knowing that the deletion of 934 BP involves exon 1 of the hint gene, we have no clear evidence that the genome rearrangement also extends to the LYRM7. In conclusion, the complex rearrangement in the two SIBs could have been overlooked if the phenotype had not been evaluated as well. NGS panel can provide specific genetic diagnosis for a subset of patients with CMT disorder. But despite this advancement, many patients with no or suspected CMT disorder remain without a specific genetic diagnosis. We just listened this morning that continued advances in genetic testing, such as multi-omic technology, together with better understanding of genotype-phenotype correlation, will further improve detection rate for patients with suspected neuromuscular disorder. However, as this case highlights, clinical assessment must continue to be of primary importance in guiding the initiation and interpretation of genetic analysis. It is interesting to point out that neuropsychiatric manifestations, although present in few cases, are part of the picture of hint1-related neuromyotonia. On the other hand, LY or HAM17 involvement must still be verified using West data and/or by RT-PCR, even if it causes mitochondrial complex 3 deficiency, that is an autosomal recessive disorder whose characteristics are not present in our patients, and be characterized by progressive neurodegeneration and episodic acute neurological decompensation associated with febrile illness. And sorry for my English, and thank you very much for your attention.
Thank you, Buya. Can you hear us?
Yeah.
Okay, so good. Any question from people in the room? I just want to check. Sorry, one thing online. Okay. Yeah, I have a question actually, and how are you doing the optical genomes? Do you have in-house any?
No. We have collaborated with Basta University's Dottoressa Bonaglia.
In Milan, basically.
Yes.
Yeah. And are you sending them now all the unsolved cases? So how are you, let's say, using this new technology within your pipeline? For what?
Sorry, I don't hear you.
So what is the idea? Are you collecting all unsolved or a number of unsolved cases?
No.
To test them?
No. Only this case
Because of what you observed.
Yes.
Manual inspection, you mean?
Yes,
yeah.
Exactly. We want to be sure of this rearrangement. Patient also, we have studied also array CGK array, and was negative. So we want to study in depth this rearrangement, and we have started this collaboration.
Yeah, thank you so much. I guess here the key point was the manual inspection, which was a crucial element. Yeah. Otherwise, you would have missed most likely the diagnosis. Yes. Okay. Buya, thank you. Can I ask you to please stop sharing the screen so that? Yes. Sorry, I don't have the program. The next speaker is Sarah. Sarah, you have now the old version because this is, of course, not online. Do you? I don't know. You need, of course, a USB stick.
Okay, so the one that I sent you.
It's not here because.
Oh, okay.
So we can, yeah, we can maybe move on and then have Sarah. Yes. So who is the next after Sarah?
The next it will be
Victoria, I guess.
Yeah.
So Victoria is from Helsinki. I guess you can introduce yourself, which makes things easier.
Yeah, so.
Yeah, if you can come here so that they can see you. Wait, I have to check that. Sorry, but. What you are sharing? You are not sharing this now. No. Now you are sharing this. Please.
So, hello, my name is Victoria Lilbach, and I work in the CoMPaSS-NMD Research Center. I'm gonna present the topic analysis and reanalysis of unsolved neuromuscular disease singleton cohort with gene prioritization. And as mentioned before, Peter told that I have an interest in AI. Gene prioritization in this case is not exactly AI yet, but it's a machine that helps us to get more away from the manual labor in molecular diagnosis. I am planning to work more with AI in the future. So I guess this is not needed here. I want to break down the title. So I mentioned singletons in case it's not a well-defined term. It's patients with no relative sequence, so we have no way to segregate the DNA data. And then analysis. The normal analysis pipeline is represented here from genome data to variant calling, annotations with population frequencies and variant pathogenicity scores, and then interpretation with the ACMG guidelines compared to the patient phenotype. And where bioinformatics solutions step in, they step in to automatize and standardize this analysis to gain the molecular diagnosis. So, how does it work in detail? So we have used for gene prioritization this tool Exomizer, which has been around since 2014. And it takes as input the clinical data with the list of variants in the VCF format. And the clinical data needs to be translated into machine-readable human phenotype ontologies. And together in Exomizer, there's a calculation of variant pathogenicity, taking into account tools such as Rebel and MVP, and then population frequencies and what is known about the variant from before, from ClinVar. Then for the phenotype, it's taken into account by checking what is known in OMIM already, but also comparison to animal models. Then protein-to-protein interactions are also considered. These generate a variant pathogenicity score and then phenotype relevance score of the gene where the variants were seen. And the variants in the VCF file are ranked according to their relevance to the disease. So how does it work? So based on literature, the causative gene and its variants are seen in the top 10. So in the first 10 findings of the list in 80 to 95% of cases. And this reduces the manual inspection of the variants significantly because the list of variants that can be considered can be in hundreds or thousands. And 80 to 95% could be found in the first 10. And it also has a potential to find novel disease genes as causative. And there's a few publications that have successfully used Exomizer to detect a novel disease gene, not yet associated with disease. So it's a great tool that automatizes and standardizes the way we analyze patient variants based on the literature. Nevertheless, we had a few more specific questions when we wanted to utilize this in the molecular diagnosis pipeline of neuromuscular disease. So our first question was, does it work as well with neuromuscular diseases, even with singletons? And the answer is yes. In our study, we had 117 already solved cases that we input into Exomizer, and we could get in the top 10 rank 97.4% of these cases. So this would have been solved in the first 10 genes prioritized. And this was without any segregation data for the patient.
Just ask,
so yeah.
The 117 cases and the genes, would just be interested to
yes.
know a bit, how rare these diseases or how common the variants or.
Now I don't have specific numbers on how rare the variants were, but they were according to the gene panel from the, I forgot the gene panel name for now.
Yeah, it's markup. So there were the solved internal cases, plus which are maybe mainly adult cases with, distal, usually phenotype and already known genes, plus an LGMD cohort from Naples, from Vincenzo Nigro's lab, plus a congenital cohort from Pisa, Filippo Santorelli. So kind of mixed, but all known, and the classic genes, let's say, of course.
Yeah.
how does it compare if you just do it with a panel of genes? So will you get the same 10 genes at the top if you do it in an NMD panel? So if you do an in silico analysis of your exome data with a list of NMD genes, would you still have your 10 candidate genes at the top?
Can you customize the pipeline so that it only works on selected genes?
Yeah, so the Exomizer, you can define which genes you're interested in.
We didn't do that, but I think it should work even better. We can try it.
Yeah, this was more like a test for the sensitivity. If we just input the VCF with minimal effort, we just input it and check what does it give out. We were happy to see this number.
But these are easy cases. Oh,
Then we had then we had another question was to reanalyze a large cohort, do we need to generate patient-specific HPOs, so human phenotype ontologies that would describe the phenotype in detail? And this we concluded that we don't necessarily need to do this. And one of the main reasons why we wanted to test this was because we don't always get a comprehensive phenotype when we get the patient samples, which is a problem, of course. But tested this by inserting the VCF samples together with 3 parental HPOs, just generally describing muscle disease. So difficulty in walking, abnormal muscle fiber morphology, and muscular dystrophy. And there was no significant difference in the performance of this. Actually, so you can see here is like you can barely see the difference, and the p-value is not significant for the difference. So, and this might be a feature of neuromuscular diseases having a lot of overlap in phenotype. So this might be specific only for neuromuscular disease. It might be that different diseases need a specific HBOs. Then we had another question, can we trust to find novelties in an unsolved cohort? And there was already publications on this, but we wanted to test it in the specific context of neuromuscular disease. And yes, to some extent, we used truncating variants inserted into candidate genes predicted by a previous publication, and 57.1% out of 35 mock cases were in the top 10. So not as convincing as the solved cases, but definitely giving us an idea that we could find novelties. And we also wanted to know, because we inserted biallelic truncating variants, was it just because they were so deleterious that we got them, or it was because of that? But actually, when we compared the parental HPOs against misleading HPOs, so we describe a completely different disease, a renal disease, we could notice that there was a significant difference, and we could not get these genes in the top 10. So the protein-to-protein interactions helped us in getting the variants in top 10 rank. So then, how did we use Exomizer in our lab for a cohort of singletons? So the first 3 steps are the basic gene prioritization pipeline. We input samples, Exomizer does calculations, and then we get the ranked list. But because we had a singleton cohort, we merged all the results together and added values such as reoccurrence of the gene, reoccurrence of the variants. If there was a variant reoccurring more than 10 times, we call it like false, because we don't expect to see that many. And then genes that were shared, we checked them with a bit more phenotype data if these patients have the same and similar phenotypes. And then we could conclude causative or discarded. And this could be done annually to check for the variants. And I noticed my time is up. So very quickly, did it work for us? Yes. With novelties, we need to filter a bit more because it's very sensitive to variant pathogenicity. So if we input a variant calling file with no filtering, it will call anything that's not seen biologically. So all false calls will be seen there. And in our cohort, we had a handful of possible molecular diagnosis found, but our cohort was small. And as told earlier, we might have a cohort that doesn't have Mendelian disease. We might have more like diagenic causes in our unsolved cohort. So for the benefits, this work automatizes, standardizes, and reduces off-target variants when you take a cohort into account. It supports novel gene hunt and ensures no cases are left unsolved due to lack of time or resources. So some future perspectives mentioned here, and limitations mentioned and future perspectives. And then lastly, to conclude, machines and humans, when we work together, we can give more accurate results than working alone. Sorry for going a bit over time. Thanks for your attention.
Thank you.
There is still time for one question. Good for one question. Please, Johan.
Thank you for your presentation. I have one question about dealing with that low quality schemes, because you said the data requires some kind of cleaning to avoid low quality results to better the system. So how do you deal? You have 270 patients or samples, and then there is a probability that for one particular sample, some of those loci will be of low quality. So how do you deal with that?
So if I understood your
How
question.
did you get rid of the low quality?
Yeah. So in first, first we started like just inputting the VCF, analyzing them as they are, but we noticed that the top 10 results were enriched with these variants that were called with maybe 10 reads. And we had put the limit there, but why were they enriched with that? Why were most of them? And we that 30% of our results were these really low call. And then we checked the original VCF, so it was only 8% of all the variants seen in all the samples were this. So we deduced that this is just something we have to filter more strictly. So we increased the limits to get rid of these variants that we maybe don't trust.
We accepted the higher range, I would say, of false negatives, but we had to increase the threshold in terms of that.
If particular variant doesn't fit into your schema, then it was no variant at that position for that person. You excluded it.
Even if the low quality, if it was covered by less than the threshold, yes, we had to accept that. Otherwise, we should have worked with a lot of. No.
Thank you.
And the next speaker is Sara Pini from Modena. Sara, just give me 1 second. Then you can introduce yourself. I trust you. What will be there? Let's see this, and we'll do this. I will hold images for a sec, share directly. This. Please.
Thank you. So, good morning, everybody. My name is Sara Pini. I'm a second-year PhD student at the laboratory of Professor Salvatore in Modena. And today I'm really excited to share with you some of our latest results. As the speakers before me extensively demonstrated, hereditary neuromuscular diseases are a wide group of conditions that lead to neuromuscular weakness and are associated to a wide spectrum of phenotypic expression. and still represents an important diagnostic challenge. The diagnostics of NMDs were long relied on the DNA molecular analysis with the idea of associating the impairment of one gene function to one phenotype. This led to the identification of more than 600 causative genes that often are identified in patients with the same phenotypes. But yet there is currently diagnostic uncertainty when we talk about NMDs. So all this consideration led to the idea that maybe NMDs rely on a more complex molecular interplay of many factors that we still have to determine. And indeed, the skeletal muscle is a complex system, and for the homeostasis of this complex system, many interactions, the equilibrium between these interactions are important. So our idea is that maybe instead of looking for a single gene to be imputed for the disease, we could look for an accumulation of variants with variable effect, even lower effects, that impair a function, a structure, and lead to the phenotype. In Modena, in particular, we study facioscapulohumeral muscular dystrophy, which is a common inheritable muscle disease with a prevalence of 1/20,000. And this is, in fact, characterized by a wide variability in terms of clinical expression and age at onset. And in Modena, we created this clinical comprehensive evaluation form to be really able to finally describe the phenotypes of the patient. In particular, we described 4 categories. Category A, which is the classical phenotype with involvement of facial and shoulder girdle muscle. Category B, which is the incomplete phenotype with the involvement of either facial or shoulder muscles. Then we have category C, which includes healthy individual, and category D, which includes FSHD subject with other uncommon features. Concerning the molecular signature of FSHD, FSHD has been historically linked to the 4q35 locus, and 2 genetically distinct forms exist. FSHD1 is associated to the presence of a DRA, which is this D4Z4 reduced allele, meaning that there is a shortening in number of these tandemly arrayed D4Z4 repeated elements. Another form is FSHD2, which includes 5% of clinical cases. In these cases, we do not have the reduction of the number of D4Z4 elements, but we have mutations in chromatin remodeling factors such as SMCHD1, the NMT3B, and RIF1 that lead to a reduction in methylation of the locus. In both models, what we obtain is a transcription of the repression of the locus that leads to the toxic expression of nearby genes. But another number we have to keep in mind is that looking at the general population, and we looked also to the haplotypes from the Human Pangenome Project dataset, which are healthy individuals, the D4Z4 reduced allele associated to 95% of FSHD cases is present in 6.7% of the general population. So how can we explain a disease which has a prevalence of 1/20,000 with such clinical variability with a genetic defect that has the frequency of a common polymorphism? It is clear to us that we have to consider the interaction and the interplay of other factors with different effects that can be genetic, epigenetic, environmental factors. So to test our idea today, we'll present you a practical example. This is a trio from the Italian National Registry for FSHD. The program is a 20-year-old male. It is category B1 subject, so he has principal involvement of the shoulders, and there you can see the description of the neurological evaluation. He has a score 6/15, so quite a relevant impairment. The parents are healthy. In this family, there is no D4Z4 reduction allele segregating. There is no mutation in the chromatin remodeling genes associated to FSHD2, and there is no reduction of methylation level at 4q35. So neither FSHD1 nor FSHD2 molecular signature. So to further characterize this case, we decided to perform whole exome sequencing on the 3 individuals and to analyze data guided by the analysis of the family. So with the idea that there could be something inherited in a recessive mode, so homozygous variant in the child that were heterozygotes in the parent, or compound heterozygote variants, Or in addition, we also made the hypothesis that there could be a de novo occurrence, so de novo variants in the child that were not present in the parent. And all this with the clear idea that there could be a multiple hit hypothesis, so a combination of a certain number of variants that in the child finally determine the phenotype. So this is what we did with our exome sequencing analysis. We started with standard pre-processing. So we performed alignment, quality assessment, variant calling, and annotation. Then we performed an initial step of filtering, of quality filtering, let's say. We decided to keep only those variants who had at least low impact according to VEP. And we decided to keep only those variants for which the genotype quality was higher than 20 in all the 3 individuals. Then we perform a gene scoring step that I'm going to explain in a minute and a functional analysis. Concerning the gene scoring step, we wanted to obtain a ranking of the gene based on several quality and functional characteristics. In particular, if for each SNP we identified, we assigned a score based on the genotype, so 0, no variant, 1, heterozygous variant, 2, homozygous variant. Then this value was multiplied by a number that correlates to the impact. So the higher the impact, the higher the scoring. Then we multiplied for the complement of the allele frequency. So the higher the frequency of the variant, the lower the score, because if a variant is really frequent in the population, it would probably have a low impact, let's say. And we multiplied by the coverage of the variant. The mean was performed for all the variant in the gene, and then we also multiplied by the normalized gene length, as longer gene may have potentially more variant, but it's just a probability. And we multiplied by the complement of the percentage of that gene covered by low complexity regions. And all this was performed, as I said, because we wanted to include both functional and quality observations. We decided to perform a scoring, a ranking, and not to set threshold, also to be as much inclusive as we could with the variants. Concerning the functional analysis, this is quite preliminary, but as we wanted to assess if there was an accumulation of variants in the child that could explain the phenotype, we decided to select those variants for which the score, those genes, for which the child scoring was higher than the score of the parent with the higher score. Considering that both parents are healthy, the child must have a score higher than the parent with the higher score. And this allowed the selection of more than 1,000, those are genes, not variants. And then we perform a functional notation using David. The most interesting terms we tried, in our opinion, is the KEGG pathway, cytoskeleton in muscle cells, the biological process of cell adhesion, and the molecular function of calcium ion binding, all with a really high statistical significance. And here, just an example, I'm going to show you the cytoskeleton in muscle cell pathway. Here you can see the genes that were included in these pathways, and as you can see, roughly half of these genes have also a really high score in the child. So this results may lead to the hypothesis that the phenotype in this subject may be due to an alteration, for example, in the interaction between the sarcomere and the extracellular matrix, that along with the cell adhesion term, let us think, obviously we will need further functional analysis, that there could be an impairment in these functions. So for example, in myoblast fusion, let's say. So in conclusion, what we want to point out with this example is that the study of complex diseases require the evaluation of complex interaction, considering also the different impact of the different variants. What we think we will demonstrate is that the comprehensive and unbiased examination of the complete genetic background of individual, along with fine clinical examination and family analysis, can allow the identification of relevant insights to explain the phenotypic outcome in the patient. Obviously, we will need further refinement of this of our system, and so also questions and suggestions are really well accepted. And finally, what is our vision is that once we can validate this method, this has the potential of a broader application to complex diseases, all complex diseases, as it don't rely on the phenotypic description. With this, I conclude. I want to thank you all, the group from the Miogen Lab in Modena, Professor Joanna Polanska and Alexandra Suwalska for all the computational analysis, and Dr. Maria Grazia D'Angelo for the clinical part, and all of you for your attention.
Okay. Thank you so much. Thank you so much, Sarah. Any question for Sarah? Yeah, one. And do you have RNA, and are you planning RNA-seq on this? How doable will be to match RNA-seq data then with genomic data to check if these pathways really are also from a transcriptional point of view dysregulated?
Yeah, surely. I mean, it would be really important to have RNA sequencing on the muscle, also, for example, biopsies, to further characterize the case and understand if the hypothesis we can make based on the data is really relevant for the phenotype. This is part of the functional analysis we have to do after this. It is just a guide.
Any other question? Curiosity?
I don't know if there's some question from the
sorry.
from online. There's not, but maybe we can ask to people to.
Yeah, we can stress that. Of course, you can ask questions also online, and we have a speaker, so you can really just unmute yourself and ask a question or write it down in the chat. But if not, we will move on. Thank you, Sarah.
Thank you.
Please. Yes, sorry, just a second. Survive. Your presentation is this. Yes.
There's one question actually.
Yes, please.
So Giselle Bon, SNIPE method to rank genes still need to validate impact on functional levels.
Yes, I mean this. Sorry, this will obviously be fundamental. We are going to also improve this method. For example, I think that will be really relevant to in the functional analysis part in silico. I mean, to test the enrichment of pathways, also considering the ranking of genes. So in order to prioritize those pathways that not only are enriched, but are enriched in high ranking genes, for example. And obviously then we will have to test functionally.
Thank you, Sarah.
Thank you.
Sam, want to go for this? Please.
I need to go forward with.
No, everything is fine.
No, to move forward.
Yeah. Just.
Oh, this. Yeah. Okay.
Or you can click here. Maybe it's
better.
Yes.
Okay. So hello everyone. My name is Michael Obach from Tecnalia in Spain. What I present now in the next 8 minutes or so is basically reflected in the deliverable D53 that we talk about this afternoon. What I want to do now is to explain the concept also for the people that are not part of the core partners here, so that people who are listening and are connected the first time to us know more or less what we are doing here. For that reason, I'm rather on a conceptual point of view. So I quickly introduce to the problem, why we do federated learning, the approaches of the project, what do we do in this project, what is federated clustering, where the emphasis is in clustering here, I talk about practical aspects in the project and also an outlook to sister projects, because we're not the only ones who do federated learning in this field of neuromuscular disease. Sorry, not neuromuscular diseases, but diseases in general. So the problem here is, well, our aim first, let's start with the aim, to stratify clinical, histopathological, genetic, and MRI data of people who have hereditary neuromuscular diseases. And then we have several European clinical partners here, 6 who share that data. And the problems with these data is manifold, but 2 major problems are: first, raw data sets can be huge. So we're talking about gigabytes or even terabytes of data that we have to share and send over the internet, store, back up, and so on and so forth. Then most of the processed data are special categories of personal data. That is regarding the General Data Protection Regulation Article 9. So these are not only personal data, these are special categories if we talk about genetics. And they need to be protected all the time. And the approaches that we take in this project is first that we have dedicated a whole work package dedicated only on ethical, legal, and regulatory frameworks. So we try to assess and minimize the risk for patients, so-called data subjects, another language to learn here, and comply with the GDPR and other laws and regulations, national regulations, and so on. And we have also an ethics advisor. We have ethics committees that we talk to and that guide us. And one strength in our, well, it's best practice, but to remark that our data is pseudonymized. It's not really anonymous, and this is an important concept here. So to focus on this talk, it's more about that in parallel, so that there are 2 pillars. On the other pillar is the design and implementation and also testing of methods for so-called federated learning. So this is a subcategory of machine learning where you have several places, several so-called clients that not share their data, but share parameters of the models they learn. You see that in the next slides. So there are several of them. So on the clinical sites, we do pre-processing. Once we apply this federated learning, then the idea is that each of the sites can pre-process the data. In reality, now, as of today, in Silesian University of Technology in Poland, these steps are done. But in the future, or in other projects, if we generalize to other projects, then we want to do that. We want to be able to do that anywhere, in any place, in any hospital, so that we don't have to share personal data any longer. And in the special case of federated clustering, we have basically, or we can represent each cluster, each group of patients that have, say, similar symptoms, that have a similar symptology, or in this case, we only assume that they have similar phenotypes. We know that they have similar genotypes, that have similar genomes, that we have to represent them by cluster centroids. These are these dots here in these point clouds. These represent each cloud. I'm running out of time. No? But, 5 minutes more or less. Then the idea is that we share with the central server, in this case probably in Poland, a central server, only the centroids, only the weights of the models that we build locally, and share them and aggregate them in one place. And then we do a clustering of the centroids in Poland or in a central server, and feed these centroids back to the initial points that we call clients. In this case, it could be up to 4 different places. Yeah, no, I'm clicking on the
Yeah,
wrong
also
one.
here you can use.
Okay, that's better. Yeah. What did I? Yeah, okay, then we have also some practical things. So it's possible in theory, at least, that some centers, say for instance in Strasbourg, don't have the same groups of selected genetic vectors than say in Pisa or in Italy or in Newcastle. This is possible. Then we have also to represent these clusters by data points. So this is one practical problem that we have. And also regarding privacy, for instance, it is possible if you have small data sets that one cluster is represented by less than 2 people. So knowing the cluster center, if you have only 2 people or even 1 person, then you know exactly who the data of that person. So then you have a problem regarding data privacy. And to come up with these special cases is also part of our aim and our problem solving. Well, then there are some practical issues also that the approach of the project is also to be safe and to have a main track. We do everything classically in one track, the main track of the project in Poland, and federated learning is only a second track that we do here. So it's in parallel, and we avoid risks and delays. If we had designed our project going only directly with federated learning, we could have failed if there are problems with federated learning. Then one thing we suggest that we simulate this approach with what they call containers. So there's a containerization, which is rather computer science stuff. I don't want to bore you with that. So there's one software that is called Docker, and we want to implement that in Poland. This is for the next couple of years. It's easy and it's elegant. Then one of our aims for the next deliverable is also to compare the quality of the outcomes regarding clustering, doing the standard approach in the main track and in parallel with the federated learning. So which one is better? How much better is it? How much more complicated is it? Does it pay off? These are main questions to that. And then I want to, 1 minute, that's perfectly 1 minute. So just to mention that on the 10th of June, I represented our project here in a roundtable of other projects that got funding from the same topic from the European Commission. And they also tried to stratify data and come up with new computer models for that. And they also, many of them, apply federated learning. And so there's the aim to collaborate also in this sense. So there are projects about rehabilitation, cancer, rheumatic issues, stroke, atrial fibrillation, respiratory diseases, urologic cancers. And the idea is to come together and share good practices and share outcomes. That's it. If you have questions, then
thank you. Thank you so much.
Thank you.
To account of the opportunity given from the federated learning model, what's the gap and the weaknesses from the European Union legislation and the national one you are getting through? If you find some gap, maybe you know.
Well, actually, I don't think that if federated learning is done correctly and well, you don't have to share personal data. As I said, there are issues like, for instance, if your centroids are too small, then you may have things. But I wouldn't call that gaps. We just try to overcome or avoid any things with GDPR. I think this would be a reply.
And, do you think that the national legislation could be something that will stop the process or will locked in certain times, and because national legislation for sure are working by themselves, depending also from what the European legislation said, but sometimes can be not working very well together. So did you find in your experience some issues like that, and if there's something that you could suggest also to other people when are working and implementing federated model?
No, indeed, we didn't find any important national exceptions or issues regarding the European approach. And as I said, the aim of federated learning is just to avoid, to circumvent, or avoid is the better word, circumvent any issues of that. Because if you do the classical one-site approach, then you have to move the data, and then you have the whole spectrum of issues that you may have. Needing.
You have an online question?
Yeah.
Online.
When dealing with rare diseases as neuromuscular disorder, it would be a problem not to include data of 1 to 3 patients from a node. Privacy protection.
Okay. Yeah. You may lose very important cases if you reduce too much. I mean, if you have in your data set only 1, 2, or 3 people, as the definition suggests, rare disease, then you may lose it, and I see the point.
We can hear you. If you want to add, we can hear you.
Yeah. No, that's the issue.
Please.
Yeah, please.
No, it's just a comment that come to my mind when you presented. I fully understand that for privacy protection, when you deal with so huge mass of data, that you need to exclude those cases. But for a lot of neuromuscular disorder, we are facing ultra rare cases, and those will never get access for comparison if you don't match them from a different center. That's the limit, and we might need to go over this issue at some point, at least for these rare cases.
Yeah, you're completely right, and this just somehow or motivates also meetings like that, because we as computer scientists didn't get that very good and almost evident thing. If we talk about rare diseases, you cannot exclude rare cases. And for that reason, we have to come up with a solution to that. So I suggest that if in this case we detect there's a cluster with only very few rare cases, or cases that are rarer than others, then we should mark them and study them out of the scope of federated learning. Then experts can look at these cases and do what they need to do with this singletons or whatsoever approaches. We cannot discard them. That's the take-home message I take from this. We should never discard them, but discard them perhaps for the federated learning. So we should analyze them, but perhaps not use them for federated learning. Or we must use other possibilities to protect these data if we want to transmit them. You're right. Thank you for that.
Thank you so much. Yes, we can move to the last presentation. Yeah, we can discuss them.
Yeah. We discussed. We have the whole day to discuss.
Thank you so much for the comment. So the last speaker is Professor Santorelli. Thank you so much, Filippo. He understood it was not the easiest.
It was a long journey.
Yeah, we have.
Okay, one would wonder why you should take a Norwegian Airlines stop in Stockholm to come to Finland. Well, nevermore. Yesterday we had a terrible flooding in Pisa. The airport was completely full of water. We had 2 hours delay. We missed our flight connection from Arlanda. Alessandro and I had a very comfortable night in the airport because everything was booked. There was horrible delay everywhere in Sweden. So then I missed the venue. I went to the villa.
But you saw it is nice.
Yeah, but finally I made because of motivation. Okay, so motivation was what we had behind the INGENE project. INGENE is an experience we had as a regional health system in Tuscany to build an integrated multi-parametric system to identify diagnostic and prognostic parameters in neuromuscular diseases. How does this one?
No, with it's yeah, so you have to go.
Oh, okay.
Yeah, we could do this.
Okay, this is a very, yeah.
Right. Yeah.
InGene is based on the concept of electronic health record, that is a tool through which citizens can trace and consult the entire history of their health. And this is what is behind the new medical record that Regione Toscana and other regions in Italy are trying to build, and was mainly relying on Health 360 framework that was a multimodal, scalable, highly customizable software platform. So it was a platform built by informaticians to collect information in heart disease. So the challenge was to adapt Health 360 to neuromuscular disorders and to use as a new tool to collect a bulky number of information from patients and try to make 1 + 1 = 3. So to have higher level than the simple sum of different components. InGene was built in 2016 as a proof of concept platform. We had initially a small hub collecting information from a single clinical center, and then we adapt to all other neuromuscular centers in Tuscany: Pisa, Siena, Florence, combined with 2 informatics centers, IT centers at the National Research Council, and 1 small company providing us with digital sensors. Out of the many modalities we were collecting: clinical information, physiological tests, electromyography, MRI, muscle biopsy. We had some easy way with the clinical and medical record. We were not able to build a solid infrastructure for genetic and muscle MRI. We are still behind in muscle biopsy data, EMG, and collection of information on clinical trials, and had very limited information on digital data. So the idea is to have a multiple layers, integrate the multiple layers, very ambitious because it started from a different platform, adapt the platform to the needs patients with neuromuscular disorders, including patients with Charcot-Marie-Tooth and spinal muscular atrophy. So collection of very broad number of neuromuscular disorders. And this on your left-hand side, you can see the different times in points in time when you had achieved the different layers. So far we have, at the end of the project, 2024, we had collected very large number of patients with neuromuscular disorders in a very solid layer from medical, family, and neurological examination. We had a very robust layer for functional motor scale. So we collect all kind and automatize and also harmonize between centers the use of the tools for functional motor scale, starting from the 6-minute walking test to the other for spinal muscular atrophy to Duchenne muscular dystrophy. The collection of genetic data and muscle MRI were very at the beginning, so we did not have a very robust algorithm. And so it was also for muscle biopsy. For Digital data, I will show you just two examples of what we have done. They are still in the beta version, so they are not able to be translated to patients yet. This is the PhysioTest. The PhysioTest is a layer for collection of physiological tests, so clinical scale. Basically, the operator can handle the record of patients, trace the longitudinal retrospective information, get information from each time point, so each minute, just to measure also fatigue, and to assess how the patient performed in different 6-minute walking tests in consecutive assessment, and also comparing different disease categories for a specific test. This is one example. We had also several more physiological tests that we call physiological tests, but was just because comes from physiotherapists. So everything was handled by physiotherapists. The other example is on the base of digital sensors. We had a goal to measure precisely and objectively muscle force. So we create a bracelet for the upper limb and electrogoniometer for the shoulder and the lower limb, for the hip, basically, just to measure correctly the force and combine the wearable sensors with graphical interface for data acquisition. This allows the operator to monitor the difference in the muscle force between different muscles, and also how different operators can test patients and achieve in a very objective way the individual weakness or strength. This is in Automa 2.0, is still in the beta version. But we tried, and it worked in a few patients with limb-girdle muscular dystrophy. And I think also in also some children. I don't remember exactly. The other way is to build a sort of, say, magic shoes, something that we can use for digital assessors of walking, like APDN, for example, just to monitor the way when you walk. This was precisely intended for patients with Charcot-Marie-Tooth, and also for patients, ideally for patients with tibialis anterior weakness. And the way to measure how you behave in a sort of walking analysis, but perform with digital sensors in your own shoes. So the goal is to have something that the patient can handle at home, that you can record from home-made measurement, and then you can monitor in an individual patient for a long time. So to conclude, it's still in development, although we have no fund left for this project. But create IT-based tools that can be pivotal in supporting researchers and clinicians in data collection. If we go in a very streamlined, what is the strength? What are the weaknesses in this project? I would say that it was difficult to change standard procedures, the way how clinicians handle data, how clinicians collect information from patients. even harder was to harmonize multiple centers, the way people should work together. Third weakness, I think the most important, there was no co-editing in definition of the endpoint. Okay, endpoint.
Sorry, I mean, you can continue.
Okay. 2 slides, 1 slide. No co-editing with patients, with patient association, and there was no anchoring to the patient need. So we cannot really say that what we are measuring are important to patients and are measurable as patients progress. Of course, we have so far a collection of rating scales, but the idea is to integrate and to have a sort of super test or super score system to measure progression in patients. And this was not done together with patients. The advantages, the strength that we can have now a single medical data repository. In Regione Toscana, soon we will have a harmonization in different clinics using also InGene as a part of the story. You can combine multiple layers, as many as you want. A bulky combination of multiple modalities can allow you to have integration. Better integration means also development of new outcome measures. And lastly, not less important, working with IT offers you the possibility to achieve different support, different areas where you can ask for money, patients association, IT supporting group, and of course, the health system, and why not Europe? That's it. So I'm ready to take questions.
Thank you. Online. Participate.
But I don't know if because come back to the directed learning, there's something new from
Yeah, we can go back eventually to this. Let's discuss.
That is for Michael.
Yeah, we can go back. I will first focus 1 second on the discussion on Filippo's presentation. Any question? Yes, please.
I have a question and basically a comment. I don't know if it is a comment. I think it is a good experience that we can use in order to try to avoid or to ameliorate the points in order not to get stuck.
Yeah. I guess we had the first experience of HAL 360 that was a very preliminary IT framework used only for patients with cardiomyopathy. Then we modified, improved with InGene 1.0. It was a proof of concept where we attempt to transfer information to patients with neuromuscular disorders, mostly children. So that was mostly patients with spinal muscular atrophy, some congenital myopathies, few children with Duchenne muscular dystrophy. Then we built a 2.0, spreading to other centers. So tackling the difficulties in harmonization between centers. Usually you say, well, you should fill this form and you get back 10% from one center, 50% from the other center. So there is the level of harmonization is still difficult. So I think our experience can be instrumental to CoMPaSS because we know what we should avoid. Okay, so in somehow we should try to improve our objective, the goals, what we are supposed to do. Okay.
Yeah, thank you very much, Filippo. When I saw the magic shoe there, I was also wondering about the fragmentation that happens now in, whether it's a magic shoe or a smart sock or a clever sensor, or I mean, there's so much diversity. Everyone now starts to have their own digital readout of movement. With assessment, at least, we have standardized. We use the North Star assessment for Duchenne or performance of upper limb but with these digital technologies, I see a real that there's actually complete fragmentation.
Yeah, you're right. You're right. And I myself use 3 different digital systems to measure walking in 3 different projects with 3 different PIs from 3 different countries. And everyone says, well, mine is best.
Yes.
Okay. So
in a way, for all these projects, I think the elephant in the room is something completely different. It's time and manpower. So what you need to have all these readouts done very well is you need a lot of time. And we have less manpower in future. So therefore, technology needs to help us really to save time. So therefore, what we need to do, and that is one of the topics here as well, we need to do it easy.
Yeah.
So that is doable within a normal visit of a patient in your daily clinic routine. If it's beyond, no one will use it because we don't have the time. No one will pay for this. So therefore, it needs to be done really in a 20-minute setting. And that's the difficulty we have. And here technology needs to support us. So having this done easily.
Yeah. But technology is also intended to measure things that we cannot measure in the clinic. And to have, if we work on multiple data, multiple modalities, we have tried to handle it, to use in the best way big data, the more we get, the better.
Yes.
So
but still in a certain time frame.
Yeah.
Otherwise, it will not be done.
Our
so then you
experience,
start with having
our
the
experience
neglected
was
data
to
set.
give patients small exercise to perform at home and to see whether those exercises, when they were performed in the clinic, were comparable. Okay. But one step at a time.
Yeah, what Benedict says is very important, but don't you think it is necessary just when we want to reach a certain goal to identify a person who will be in charge of reaching that goal? Because it is really true that time and manpower is extremely important. But on the other hand, I think it is also very important
That's right, but that's more or less for a project. But what we want to go, the higher ground is here having this for the long-term situation, to cover an age, a lifetime age of a patient. And that's, so therefore we need to stratify and downsize it. So what we do, our overgrowth. So we have an overgrow in IT-guided readouts of things. We have devices and we are not sure. And what we don't do is really having a very proper analysis and getting rid of some of these things already. Say, well, this is not working. Yeah. Skip it. Don't do it again. And also with our all clinical detail defining, I think. So if we go to an approach that we can do it more on a picture-like approach. So that's always why I talk about gestalt. So if we do it really with a more complex perceptual thing, and then now technology will help us in the future. So we can do a full body scan of MRI. Of course, we are not there in all the places, but things like that. So if we really look for the higher ground, I think that's important, but reduction is the topic and not widening.
Yeah, but and I think now we cannot give going to be a long discussion, but I think it is very important to decide what is important for the very beginning, to delineate the way you work, and then you scale down, and then you review.
Yeah, but at the beginning we should already consider we need to reduce and not to overgrow.
Thank you so much. Thank you, Filippo. There is the normal question we didn't discuss. Let's take it briefly if possible, because I mean we will have lunch and the restaurant has specific.
Okay, I
Let's-
read it aloud so that everyone knows what the question is. I fully support Giselle's point. This is about rare diseases. If you have only 1 or 2 points, better points of rarer diseases within the rare diseases, there's a project that is called ERDERA, as major European partnership on rare diseases under Horizon Europe, started on 1st September for 10 years. Website will be launched very soon. In the meanwhile,
AGPRD. The AGPRD rare diseases, that is basically this framework for rare disease in Europe. I think
yeah,
more or less we are familiar with the program as well.
You have to read the message before.
Yeah,
because,
yeah.
Giselle said that as part of recently launched the EU
Yeah,
project, data, federated access to data are also under development. Maybe interesting also to connect with the leaders involved with the.
Yeah.
We
Yes,
are
of
very
course.
glad and very open with other projects.
Sorry, we missed that point, but now we got it.
Yeah, indeed. I fully support that idea that we get into contact on the task leader or work package leader level with our data project and CoMPaSS-NMD to talk about do's, don'ts, best practices, and so on, what we can do together, and also to promote the idea of federated learning within Europe. And together we are stronger. So that's the reason why we also have this liaison with other European projects. So fully support it. So that's actually one task for us to continue.
Also, I think also related to our exploitation part of the project, because also I think also your project, their project should provide also final guidelines. So maybe it's an opportunity for both projects to be in contact that final part. So thanks for catching up.
Yeah, thank you.
Thank you for your comment. Thank you. We wrote it down. I guess we will come back to you then. We can grow up. I mean, it's 11 past 12 here, so we have to stop. Thank you so much for those who attended it online. And you can reach out by email if you have any other question. There is, wait, a new message now. Yes, okay. For cooperation. Thank you so much then. And we will continue here, but I will stop now the Zoom call. Thank you.
Bye-bye.
Bye-bye.